Hi everyone, this video is going to be about preparing buffers. And remember this buffer I prepared, that one containing acetic acid and sodium acetate? The way that I prepared that was I had a 1 liter vol flask and I took some acetic acid and added it to that 1 liter vol flask along with sodium acetate, and then I diluted to the mark with deionized water. But what if I needed to prepare the buffer and the stockroom was out of acetic acid? What if I only had this sodium acetate that I could use to prepare that buffer? I could still do it if I had some strong acid. In other words, I could prepare the missing acetic acid by adding a strong acid to the acetate. So we'll do an example like that. So here's the problem. We need to prepare a buffer with a pH of 4.8, and we're going to be using acetate and a strong acid. And when we mix those two together, we're going to get the missing acetic acid. And notice the pKa of acetic acid is very close to the desired pH. So the first step is going to be writing a neutralization reaction. H plus is going to be a reactant. It's going to react with the acetate, which I'm just going to call A minus, to form, again, the missing acetic acid, or HA. So we're going to need an ice table. And again, they want to know how many milliliters of this one formal HCl do we need. So do we even know the moles of H plus that we have initially? No, that's really what we're trying to figure out. So we would call that X. And how many moles of A minus do we have initially? Well, we know how many grams. We're given the formula weight. We can figure out those moles. I got 0.189 with an insignificant 0 moles of A minus, and we don't have any HA to begin with. So now reactants are going to go down, products are going to go up, but what do we subtract? The X or the moles of A minus? Well, it would have to be the moles of X, wouldn't it? If we subtracted the moles of A minus, we wouldn't have a buffer anymore. So reactants go down by X, products go up by X. So after the neutralization, we don't have any moles of H plus. We do have 0.1890 moles minus X of A minus, and we've made the missing moles of acetic acid. So now we can use the Henderson-Hasselbalch equation and solve for X here. The desired pH is 4.80. The pH equals the pKa. That's 4.756 plus the log of A minus over HA, so that'll be 0.1890 minus X over X. So now let me ask you to think about something. We ignore these X's a lot. Should we ignore the X in this case? The answer is no. This reaction goes to completion. X isn't going to be small because this equilibrium lies to the right. Leave it there and don't ignore it. So in order to solve this equation, I guess we should subtract the pKa from both sides. I got 0.04 with an insignificant 4, and that equals the log of this quotient, and maybe we should take the anti-log of both sides. The anti-log of a log is just what you have here. That'll be 0.1890 minus X over X. So the anti-log of 0.044 is 1.1. Again, 2 digits in the mantissa means I need 2 sig figs. If I multiply both sides by x, that's 1.1x times 0. Which equals 0.189 minus x. Add x to both sides, that's 2.1 x is equal to 0.1890. And then solving for x gives 0.0897. That is the moles of H plus, isn't it? And that also equals the moles of HCl. And then one more step to get volume. The concentration of that HCl was 1 molar. So for every 1 mole of HCl, there's 1 liter. Moles cancel. And then 1 liter contains 1,000 milliliters. So that would be 89 milliliters of that HCl that we would need to prepare a buffer with a pH of 4.8. So we'll do more like this in class. Hope you enjoyed it, and thanks for listening.